Welcome. Today we are going to see a new class of equations. So we call this semi-linear evolution problem. Okay. So what is the difference between this problem with the problems which we have discussed earlier? In all earlier problems, we had this phi, this unknown, appears only d phi dt and here. Okay, and either we did not have any additive term or we have additive term, but that is independent of the unknown phi. Okay, but here for now we are assuming that this additive term also involves phi, and this could be in non-linear manner. One can think that, okay, if it is just a linear function of phi, then one can put that function inside this, operator, definition of the operator. So that is not a new problem. So a truly new problem really appears when this dependence is not linear. However, if it is not linear, then things becomes complicated also. So we are going to assume some sort of, we are going to assume Lipschitz continuity of f on the second variable. Okay, so this kind of problem, okay, so is new, which we have not yet discussed. And since we are going to discuss this, okay, so we are going to put our main focus for this. So we are assuming simpler settings here about the operator A. We are here not allowing it to depend on time t. We are just assuming that A is constant. So it is time autonomous operator here. So this is extension of IIVP, inhomogeneous initial value, initial value problem, where f of t is replaced by f of t comma phi t. Okay, so here we consider this equation. Okay, so starting point is assumed to be s. So phi of s is equal to x. Okay. And then time t is between small s to capital T. Okay, so this equation we henceforth going to refer to as SEP, S for semilinear, E for evolution, P for problem, semilinear evolution problem. And here f is assumed to be a continuous map. So f is a function of two variables, the time variable and the space variable here. So now the time variable, this is coming from the closed interval is small s to capital T, and here this x variable, this is because phi is a solution for every time t it is taking value in the Banach space. So phi of t is a point in the Banach space. So that is here. So this is a member from capital X, and the result of f or the range of f is also in capital X. Okay, so this map is assumed to be continuous in time variable t, and Lipschitz continuous in this second variable. And A is the infinitesimal generator of a C0 semi group Tt. Okay, that is also included in our assumption. Then we define what we mean by a mild solution of this equation. Okay, so here this notion of mild solution becomes quite different from earlier notions, although equation looks similar. Why is it so? Because the unknown appears here. So if we try to write down the formula for variation of constants, that f appears in that integration, but then this phi also appears. So this is not a formula because the unknown phi appears on both sides. So this is basically an equation. Got it? So here we define mild solution in the following manner: a continuous solution to the integral equation phi t is equal to capital T minus t minus s of x plus integration small s to t, capital T of t minus r f for phi dr. Okay, so that is called a mild solution to the SEP. Okay, so here since A is time autonomous, So and it's just a semigroup TT, so we are using that semigroup TT for writing down. Okay, so it appears exactly as same as we have obtained for formula for variation of constants. Only difference is that here this is not a formula, but this is rather an equation, because the phi is appearing on the both sides. Okay, so what we are going to always refer to is this integral equation. Okay, so if I say that, okay, let phi be if phi be a mild solution of ACP, I mean phi be a solution of this integral equation. Okay, so not arbitrary solution, but a continuous solution. I mean, that means phi as a function of t is continuous. Okay, now we should ask the question, the existence and uniqueness of mild solution of 2ACP. See, this is a question which we never asked before. Why? Because that mild solution was just a formula. I mean, so formula is written here. So we did not need to ask the question whether that exists or not. But here it is an important question, that whether it exists. Okay, so this equation is like Volterra equation type of thing. So if it is linear, if correct, because here this integral equation phi appears here and here, and then you have variable r running from s to t. Okay, so it is not very difficult to establish the existence theory of this equation. So we are going to recollect that thing. We are going to prove this thing rigorously, this theorem. So let me state the theorem first. Let f be a function from closed interval s small s capital T cross x to x. Okay, so this be continuous map in time t in this t variable and uniformly Lipschitz in x. What does it mean? That I mean, so f of small t comma x, okay, that as a function of x is a Lipschitz function, but the constant Lipschitz constant that is independent of this time, okay, that can be chosen independent of this time variable. If A is the infinitesimal generator of a C0 semigroup TT on X, then for every small x in capital X, the ACP has a unique mild solution which solves the integral equation. So this is the theorem. See, here we are choosing the initial point small x not from inside the domain of the definition of operator A, but from but anywhere from the Banach space capital X. Okay, so because we are not asking here for existence or uniqueness of classical solution. We are just demanding existence of mild solution. So far existence of mild solution is concerned, we can still restrict ourselves. We can just allow small x to be anywhere from the Banach space capital X, and then conclusion. There is another conclusion is that as a function of small x, where small x is the initial point. Okay, so for every small x we get a whole path phi t, correct? So this path now for if you vary small x, you get another path, because phi t is for every time it moves in the Banach space. So as a function of time, it is a path. So it's phi is continuous also, right? So we get a connected path there. So that maps small x to the path. Okay, if you vary x, you get various different paths, and then this map x to the path, so that this map is also Lipschitz. Okay, so this is also another nice property we are going to get here. Okay, before starting the proof, let us have some remarks here. So the remarks is that when the additive term f is independent of the second variable, okay, here in this case, so then this is just IIVP. Okay, so this reduces to IIVP. Okay, And then the integral equation, what we have written in the earlier slide. So this integral equation, so if f is independent of the second variable, so then it is not an equation itself. So this is just a formula. So this coincides with the formula for variation of constants. So this is the remark we are making here, and that then the integral equation also reduces to the formula for variation of constants. So proof starts. So this proof is a little lengthy, okay, but it is not tricky. It is elementary. So the main idea is basically for existence or solution of integral equation. Most of the time relies on coming up with a map which should be established as contraction, to argue that that would have a unique fixed point, and that fixed point would serve the purpose of the solution of the integral equation. So that is the line of the proof. So we start here. So define a map capital F. The map is a function, okay, this capital F. What does it do? It takes a path, okay. So path, I say path because it sounds more closer to this thing, because the function from time to x, okay. So F takes a continuous path to a continuous path. So this by this following formula. So this is basically the right hand side of the integral equation, correct? Capital F of phi t is defined as capital T of t minus x plus integration small s to t capital T of t minus u f of u phi u du. So this is basically the right hand side of the integral equation. So if right hand side on the integral equation is written as capital F of phi, then the integral equation becomes phi is equal to f of phi. So the solution of the integral equation is nothing but the fixed point of the map capital F. So that is the idea. Okay, so then the fixed point of capital F is the solution to the integral equation, and vice versa. So we aim to show that the contraction principle is applicable for this map capital F. Okay, so that is the idea. So what we do is that this is a very standard approach. So for contraction, we just need to evaluate capital F as two different arguments. Here arguments are the paths phi 1 and phi 2. So capital F of phi 1 minus capital F of phi 2. Okay, so that evaluated at t. So that is obtained by integration. So the difference of this right hand side, correct? So here I have capital T of t minus sx, but this does not depend on phi 1 or phi 2. So this term will be the same, and they would cancel each other for phi 1 and phi 2 case. So this would not appear in the difference, only this part would appear. Here in this part I have integration small s to t, capital T of t minus u, since it is a linear operator. So I would get this difference here, small f of u comma phi 1 u minus small f of u comma phi 2 u du. So now here we are now going to take the norm of this term, because these are the terms which is in the Banach space capital X. We are going to find the norm in that space X norm basically. So for this, what we do is that capital F of phi 1 minus capital F of phi 2 at t is less than or equal to, here for this integration we know that this f is Lipschitz in second variable. Since it is Lipschitz in second variable, and if capital L denotes that Lipschitz constant, and actually it's the uniform Lipschitz, correct? So capital L, the Lipschitz constant, could be regarded independent of the first variable. So write down capital L here. So this would be norm of this can be upper bounded by L times norm of phi 1 minus phi 2, okay, evaluated at u, but that can also be bounded by phi 1 minus phi 2. And then For capital T, what we do is that we take supremum from over this interval small s to capital T, the maximum of this, that is capital M. So this is finite. Why is it finite? Because capital T is a Caesar semigroup, and then since it is a Caesar semigroup of bound linear operators, so on a compact set here on S to capital T, so this is a bounded thing, so its supremum I would get a finite number capital M, so that we use here capital M. Okay, and then T minus S is coming because of this integration, because if all this constant comes out of this, then we get T minus S, okay, du. Okay, so I mean here this thing is written very briefly. This is actually obtained in two steps. One is norm of phi 1 minus phi 2 of u, okay, for each and every u, but we would like to get rid of that. We take even supreme over all possible eu, so that would give a norm in this sense, okay, in this sense, and that is phi 1 minus norm of phi 1 minus phi 2. Okay, so we obtain this inequality and we write down that as star. Okay, we are going to use this later also. So now we substitute phi by capital F of phi in the earlier thing here. Here if I substitute phi by F of phi, then I get F square of phi, okay? F of phi. Okay, F composition of phi. Okay, so here also instead of phi I should get F of phi here. Okay, so we do that by substituting phi by F of phi, we get F square. Okay, so I call this F square is like F composition F. So this, I mean, like double composition. F square of phi 1 minus F square of phi 2 of T is equal to, is for the same reason here, as we have obtained this difference, we are going to get the same thing, only except here instead of phi 1 we are going to F of phi 1, correct? So here we get integration small s to t with respect to u variable du, and here we have capital T of t minus u, f of u comma capital F of phi 1 u minus small f of again u comma capital F of phi 2 of u du. Okay, so now we are going to get the estimates and norms, etc. So here we take norm here both sides. So norm of f2 of phi 1 minus f2 of phi 2 t is less than or equal to integration small s to t. Here this norm here, and then this difference norm appears here. Norm of f of u comma f of phi 1 u minus small f of u comma capital F of phi 2 of u norm du here, and then as already you have defined capital M in the earlier slide, exactly using that capital M, I can upper bound this by capital M, and for the same reason as earlier, since this is the second variable and small f is Lipschitz continuous in second variable, uniform Lipschitz continuous second variable, so we can bound this by capital L times norm of norm of difference of f of phi 1 minus f of phi 2. So we do that, f of phi 1 minus f of phi 2 u du here, and then we get this integration sign there. So next what we do for this, again we apply this thing, correct? Norm of f of phi 1 minus f of phi 2 is less than or equals to m l times phi 1 minus phi 2 t minus s, correct? So here also we have that f of phi 1 minus f of phi 2. So there I am using the inequality star, okay, to get again ml and then u minus s and then phi 1 minus phi 2, norm of phi 1 minus phi 2, and then here this integration u is running from small s to t. Okay, so what we get is that ml. So here if we do this integration, I would get as a result of this t minus s whole square by 2. So that is written together ml. These are all constant, t minus s whole square by 2 norm of phi 1 minus phi 2. Okay, so now this thing we are, I mean, if we now take supremum for all possible small t between smallest to capital T, we get a further this thing. So so here we get, I mean, first we instead of f2, we by induction we can get f3, f4, etc., and only instead of 2, I mean, it would be 3 and 3 factorial, etc., would come due to this reason. We always would have this, and then so like there you would get u minus s to the power of some orders. So we would get fn norm of fn phi 1 minus fn phi 2 t is less than or equal to ml t minus s to the n by n factorial times norm of phi 1 minus phi 2. Here after this we take supremum over all possible t between smallest to capital T. So when we do that, left hand side is this and right hand side, that would be, t minus s is replaced by capital T so that it dominates all other terms. So this to the power of n by n factorial norm of phi 1 minus phi 2. So this is for a particular n, whatever n you can, there's no upper limit, you can make n as large as possible, but you would still get this inequality. And then as n tends to infinity, we know that this term converges to 0 because this term appears in the expansion of exponential function. So that constitutes the term of a convergent series. So this converges to 0. So given, I mean, does not matter how large m, l, or t are, this whole thing may go would be as small as possible for a large n. So so one can choose sufficiently large n so that this is less than 1. So as mlt to the power n by n factorial converges to 0 for n tends to infinity, there exists a capital N such that ml, so there is a typo, just capital T, t to the power n by n factorial is less than 1. Whatever that n is, we fix that n. Okay, then we have this relation that capital F is a map such that capital F to the power of n phi 1 minus f to the power of capital N phi 2, this norm is less than or equal to some constant which is less than 1 times norm phi 1 minus phi 2. If that holds, then we can actually apply the contraction principle. Okay, so contraction principle. So we apply now contraction principle for the function f. Using contraction principle, f has a unique fixed point. Okay, f has a unique fixed point, and let us denote that unique fixed point by phi. So phi is a function from time to x, is a path, continuous path. Okay, so this denotes the fixed point. So by this we have, I mean, although this is a unique fixed point, but by this we have not really proved uniqueness, but we have surely proved existence, because since f has a fixed point, and since fixed point is the same as solution of the equation of the integral equation, so we have surely assured existence of a solution of the integral equation. However, why does it not imply uniqueness? Because this is just one particular way to obtain solution of the integral equation. Okay, I mean, of course, if the integral equation has another solution, then one can ask that, okay, both should be fixed points of the same function. Okay, and if both are, but then it is unique fixed point. So in this sense it is saying that, but we cannot conclude from here that Lipschitz property from x to this thing. Okay, so what we do is that here now next few arguments is going to establish that uniqueness part again, and also the additional property, that Lipschitz property of the Lipschitz dependence on the initial data. Okay, so next let phi 1 and phi 2 be the solution of integral equation with initial condition x1 and x2 respectively. Okay, so assume that with two different initial conditions x1 x2, we have phi1 and phi2. So then phi1 minus phi2 of t norm, this is less than or equals to capital T of t minus s x1 minus x2 norm plus ml times integration s to t phi1 u minus phi2 u du. Okay, so this we obtained directly from the equation, because the integral equation, if I write phi1 and phi2, and if we take difference, we are going to get t of t minus s x1 minus x2, because both starts with different things. Since both starts from two different points x1 and x2, so this term survives here. Earlier, since we talked about both starts from the same x, so they disappeared, but here they are here. So norm of phi1 minus phi2 of t. Okay, but this whole thing is a real valued, correct? So real valued function of time t plus ml. So here we had this capital T minus s t capital T of t minus r f of r phi r dr. But there, when we apply the Lipschitz property and then the boundedness property of the symmetric group, and we get m and l, so we get these estimates for that line. And then again here also we apply that upper bound capital M, so we get capital M times norm of x1 minus x2 here. So here I have ml times integration small s to t norm of phi1 minus phi2 u du. Okay, so by Gronwall's inequality, how can I use Gronwall's inequality? Because now one can consider phi1 minus phi2 t as a function. So it's a real valued function, right? Because this norm is there. So this real valued function, so here also this norm comes. So this real valued function appears in both sides, and we have this inequality. So whenever one has this inequality, we have seen earlier Gronwall's inequality, that for these we can write down estimate for the solution, I mean the function which satisfies this inequality. What is that estimate? That norm of phi1 minus phi2 t is less than or equal to m times this constant would appear, m times norm x1 minus x2. Okay, and then this would appear in the power of e, so e to the power of ml, and then here this difference is t minus s, so small t minus s, but then we are taking all possible t. So if t, I mean at most it could be capital T, t could be at most capital T, so we upper bound by capital T minus s, so the right hand side becomes independent of small t, it doesn't depend on small t, so that okay, e to the power capital ml times capital T minus s. Left hand side of course depends on small t, right hand side does not. So if we take supremum over all possible small t from the left hand side, you still obey this same upper bound. So it implies that norm of phi1 minus phi2 is less than or equals to capital M times e to the power of ml capital T minus s norm of x1 minus x2. This is the same thing I just rearranged. So this norm of difference appears here, m appears from here, and then this part appears here. Okay, so by this we'll be able to conclude what we wanted with the desired Lipschitz property of the solution, I mean Lipschitz dependence of the solution to the initial point. Because x1 minus x2, if you change, that thing is changing this way. So this gives uniqueness, and uniqueness also we have opted earlier. So for example, if we choose x1 is equal to x2, both are equal, then it is 0. So phi1 and phi2 would be identical. Okay, so the norm of that would be 0, correct? So that would give again uniqueness, and also it would give Lipschitz continuity, because so here this is the Lipschitz constant, correct, of this man. Okay, so this is the end of the proof. Okay, thank you very much.